Hello everyone, welcome back to the channel. I am Sanket Singh, and in this particular video we are going to continue our discussion on the time and space complexity analysis series. This particular video is going to be the last part of our 5-part series on time and space complexity analysis, where we have discussed everything around complexity analysis right from the scratch to the pretty advanced part. We saw how exactly asymptotic analysis work, best, average and worst case of all the algorithms, and we tried to do some hands-on as well. Now, in this particular video, we are going to talk about one more type of analysis, which is called as amortized analysis. This is something that not a lot of students know about, but is very crucial for you to understand this because a lot of data structures and algorithms are actually calculated based on these amortized analysis. We are going to see that how exactly arrays work internally and do the amortized analysis on array insert operations. It's going to be a fun mathematical lecture altogether. I'm really excited for this. I hope you guys are too. That being said, without any further delay, let's just start. But before starting the video, if you have not yet considered subscribing to the channel, do subscribe it. We are going to put some really awesome content coming up ahead on this channel. So let's just start. So guys, before moving forward, there is a very important information that I would like to give you. So recently we wrapped our Elite 1.0 front-end development course, and now we have launched our Elite 2.0 advanced front-end development course. This is a bigger and a better front-end development course that you need. This course doesn't need any particular prerequisite, and we are going to take you from the very beginner level to the advanced level of front-end engineering. We have actually included projects like your own Replit clone, Wix website maker clone, right? Uber clone, and a lot of similar projects. We are going to make your own PubSub library based LLD driven projects, and we are going to make sure that you learn important front-end design patterns as well. I'm going to list down all the projects and all the important design patterns here. This is the only course that you need if you are aiming for SD1 or SD2 or SD3 kind of roles, because we are going to take everything to the very advanced level in front-end engineering. We are going to learn a lot of optimizations, and we are going to see technologies like Next.js, Redux, Zustand, TypeScript, React, and of course, the latest version of React. This particular course is going to make sure that you have ample amount of projects that you can add in your resume. We are going to make approximately 20 plus projects with different variety of complexities, engineering problems, and of course, there will be a lot of discussion around the core concepts of frontend. So what are you waiting for? Check out the course link in the description below, and you can use the coupon code mentioned in the description section to get maximum discount possible. See you guys in the cohort, and let's get back to the video. So now we will talk about amortized analysis. What is amortized analysis? It refers to determining the time averaged running time for a sequence of operations, right? So what we do here is we try to somehow calculate average running time or space, whatever you want to consider, average running time or space, whatever it is, for the given sequence of operations, right? We try to somehow take average. Now you might be thinking, okay, how is it different from our regular average analysis of asymptotic analysis, right? How is it different there? So let me talk about it. It is different from average asymptotic analysis, because here we do not make any assumption. We do not make any assumption about data values, right? Whereas in the asymptotic average analysis, we assume an overall average performance, right? So now what's the difference? Both of them look similar, right? So what's the difference? So actually, in your asymptotic average analysis, no, we take the average of an overall performance. For example, sometimes if your algorithm doesn't work well, then we don't consider them as a very bad case or something, right? We try to generalize the overall analysis in the big theta notation directly if you go directly by asymptotic notations. But if you go by amortized analysis, no, then we don't make any assumptions. Then we don't consider that, okay, there are 3 or 4 odd cases that are not going well, but overall it works well. No, that's not how we do it. In amortized analysis, generally we actually consider all of the operations, calculate runtime of each individual operation, then calculate the average without any assumption. Okay, let me repeat. In the asymptotic average analysis, we try to make an assumption based on the overall performance that, okay, the best case is something like this, the average, the worst case is something like this. Average is going to lie somewhere in between. Even if 2 or 3 odd cases are there which are extremely expensive, we just don't consider them very bad. We take an overall performance. But in amortized analysis, we try to go with each and individual every operation. We write down all the instructions required for every operation. We sum up all the instructions divided by total number of operations and then calculate the actual runtime. Now, amortized analysis is very good for those situations, good for situation where an algorithm performs some good operations and some bad operations, right? And some bad operations. So what is this some good operations and some bad operation? Let me talk about it. So you will find this definition very frequently on the internet, that amortized analysis is a good way for analyzing complexity for those algorithms which perform very good in most of the cases but extremely bad in some of the cases, right? So amortized analysis is going to be for those kind of algorithm that are going to be good overall, like every now and then operation is very efficient, but sometimes they perform extremely bad, absolutely opposite. This extremely bad situation is not going to occur like most number of times. It's going to occur very less, but it's extremely expensive. In this kind of situation, amortized analysis is very good, right? So I will show you that. Now we are going to discuss an algorithm. I will tell you that if we would have seen it with respect to big O notation, big omega notation, average notation, how we would have thought about it, right? And then if we will do amortized analysis, the story will be absolutely different. Okay, let's see. So in most of the programming languages like C, C++, Java, which are the traditional high performance programming languages, the concepts of arrays is different with respect to the new modern languages like Python, JavaScript, Ruby. If you are someone coming from the world of Python, JavaScript, Ruby, these kind of languages, so in these languages, whenever you create an array, these arrays are dynamic. That means you create an array and then you call your push or you call your append function in your corresponding language, and then you add a new element. So for example, let's say I create an array of 4 length 1, 2, 3, 4. If I want to add an element, in this array, if I want to add an element, I will just call the push function and I will add one more element 5. Then I will again call push function and I will add one more element 6. Right. So we get access to these functions like push, append, and all in languages like Python, JavaScript, Ruby, etc. These languages do provide us these functions. Right. We get a feeling that behind the scenes, we get a feeling that behind the scenes, it is increasing the length of the array only by one, right? We get a feeling like this, right? We get a feeling that whenever we push an element, it just adds one more element at the end of the array. It just adds one more element at the end of the array. But is it how it is done? Because if you go to the world of languages like C, C++, Java, in these languages, you don't have these push or append functions. Why? Because in these languages, the arrays are of fixed size. Arrays are of fixed size. And an overall computer science concept, if you see for arrays, arrays have been always of fixed size, right? So if you make a traditional array in C++ or Java or C, you will always find yourself making an array of fixed size. That means if you have created an array of size 4 in C++, you cannot just add an extra element at the end of it. You cannot do this. If you have an array of 4, that's it. It's always an array of size 4, right? But there are few libraries and there are few external solutions that are available even with C++ and Java. For example, C++ has something called as vectors. Java has something called as array lists, right? That works similar to what we have in Python, JavaScript, and Ruby. That is dynamic arrays. In these languages, we have access to dynamic arrays. If you have to create dynamic arrays in C++ or Java, then you have to use something like vectors or array lists, right? Because the traditional arrays are of same size. But again, my point being that if C++ has got vectors, which is technically a dynamic array, that is in runtime, you are able to add an extra element at the end of the array. Why you have normal arrays, right? And even if you have these vectors, array lists, and in these languages, you have these dynamic arrays, when you add an element, does that only adds just one more element at the end of the array, or it does more than that? What's the whole situation behind all of these things? That is something that we are going to talk about. So actually, behind the scenes, if you go with languages like C++ or Java, these vectors and array lists are made using the traditional arrays only, which are of fixed size, right? And even the internal implementation in these languages like Python, JS, Ruby are similar to fixed arrays only. They are dependent on fixed arrays, but they have exposed interfaces like these so that you can use these fixed arrays like dynamic arrays. So technically, Python doesn't expose something like a fixed array to you, or JS doesn't expose something like a fixed array to you, right? They directly expose something which is similar to vectors and array lists, right? Although Python has an array library, you can import the array library using which you can mimic this fixed size arrays, but not directly with JavaScript, right? So what happens is internally these languages or even C++ vectors or Java array list use the fixed size arrays only. So that is one thing that you have to keep in mind, that internally arrays are always of fixed size. They try to algorithmically do something so that you are able to add elements at the end of the array. That means you are able to expand the array during runtime. This expansion of array during the runtime is handled algorithmically, and that algorithm we have to understand. Okay. So arrays are always handled algorithmically for demonstrating dynamic nature, right? Okay. Now you might be thinking, okay, so the problem statement is, so technically the problem statement is we have access to fixed size arrays, and we have to create dynamic arrays. We have to create dynamic arrays out of it. Right, that means if you call the push or the append function, then you are able to add the element at the last of the array and all the elements remain intact. Now, what can be the worst possible solution that you can think of? Just think about it. Let's say I created an array of size 5. I created a default array, let's say of size 5. Elements are something like 2, 1, 6, 3, 8. Okay. Now let's say I have to do push 16. I have to add one more element 16. Now technically there is no space left, right? That you can add at the end of the array, right? So what can you do? The worst possible solution is you can create a new array of length 6. You can create a new array of length 6. See, this array is of length 5. You can create a new array of length 6. You can copy all the old elements one by one. So 2, 1, 6, 3, 8. And then you will be having one more vacant space and you will add 16 here. So the algorithm says every time increase the size of array. Every time increase the size of array by 1. Right? So just think about it. If let's say you have an array of length n and you need to add one more element, then what do you need to do? You need to create an array of length n plus 1. You need to copy n elements. So if you have to copy n elements, you need to apply loop. And then at the last of the n plus 1 length array, you will add your new element. Right? So can I say every push operation, push at the end of array, is going to take order of n time? Every push operation is going to take order of n time. Can I say that? Just think about it. If you have 5 length array, you have to make a new array, then do 5 copy operations and then add the new element. Now, if you have to add another element, you'll make a 7 length array, do a copy of 6 elements and then add the last element. So every time you are doing order of n time task for inserting a new element, and this is not very efficient. This is not very efficient. We can definitely do something better. What can we do? What can we do? Let's think about it. So let's say I say that instead of increasing the length of array by 1, how about we double it? How about we double it? Instead of doing n is equals to n plus 1, that is incrementing the length of the array by 1 unit, how about you double it? Let's see what improvement we do if we try to double it instead of incrementing by 1. So let's start. Let's say you have a 1 length array. You have a 1 length array. Okay, this array is empty. The elements you want to insert are 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110 and so on. These are the elements to be inserted. Okay. And here I'm going to write total operations. Total operations required for insertion. Okay. Cool. So I create a new array of length 1. I have a new array of length 1. I want to insert 10. Do I have space left in the array? So let's do one thing. Let's write one more parameter capacity. And let's write one more parameter size. What is the capacity? Capacity is how many total elements the array can hold. And size is how many total element the array is holding. For example, in this situation, when the array of the length of the array is 1, the capacity is 1, the size is 0. Because it can hold one element, but it is not holding any. Okay, cool. So you have to insert 10. Is there capacity left? Yes, we have one space left and we want to insert one element. So 10 will be inserted without any problem. So we inserted 10 with just one operation. Okay. Now Can we insert 20? Can we insert 20? No, we cannot. So what will you do? We will double the size of the array. We will double the size of the array and then copy 10 here. So copy takes one operation. In one operation, we were able to copy. And then we will insert 2. So in one operation, you will insert 20. So on a total, you took 2 operations. Now the capacity is 2. The size is also 2. Can I say that? Previously, the size became 1. Right? Now let's say you want to insert 30. Can we insert 30? Can we insert 30? No. That means we have to create a new array of double the size. We will copy 10. We will copy 20. So 2 copy operations are there. And then we will insert 30. And third insertion. So technically to insert 30, we took 3 operations. Right. So here also I'll write element. So first 10, then 20, then 30. So to insert 30, we took 3 operations. The capacity of the array is 4, but the size is still 3. See, capacity is 4, but the size is 3. Now the real game will start. Now we want to insert 40. Can we insert 40? Can we insert 40? Yes, there is space. There is capacity left. So in one operation, you will be able to insert 40. Now the capacity is 4 and size is also 4. Can I say that? Because there was vacant space left. If there was vacant space left, then I could have just directly added 40. No problem at all. But now we have to insert 50. Is there a space left for 50? No. So we will double the size of the array. Okay. So this is 4, 4, 8. What we will do? We will copy 10. We will copy 20. We will copy 30. We will copy 40. So 4 copy operations and 1 operation to add 50. So to add 50, we took 5 operations. The capacity of the array is 8. Size is 5. Now, I want to insert 60. I want to insert 60. Can I insert 60 here? Yes, because there are 3 positions left. So in one operation, you will be able to insert 60. The capacity becomes 6. Can I insert 70? Yes. In one operation, you can insert 70. The capacity is 8. The size becomes 7. Can I insert 80? Yes, you can insert 80 because there is capacity left. Capacity is 8, size is 8. Now, can I insert 90? Can I insert 90? No. In order to insert 90, what will happen? You have to create a new array. This array will be of size 16. You will first of all copy 8 elements, right? Once you have copied 8 elements, then you are going to insert 90. So in order to insert 90, how many operations do you require? You require 9 operations. The capacity is 16 and the size is 9 and so on. Can I say this is how the analysis will go, right? If we have to insert n elements, then this is how the analysis will go. Let me repeat. Initially, you had an empty array. You wanted to insert 10. You can just directly insert it in one operation. Now you want to insert 20. There is no space left. So you will double the size of the array. And now you have space. So you will add 20. So for doubling, you will first copy 10 and then add 20. So for inserting 20, you require 2 operations. But now there is no left space for 30. So we'll double the size of the array. We'll do 2 copy operations and then one insertion for 30. So to add 30, we took 3 operations. But to add 40, we were having a vacant space left, so we just directly added 40. Now we want to add 50, so we will again do the double. We'll copy 4 elements and then we will add one more element, that is 50, so total 5 operations and so on. These are actual number of operations / instructions that you are executing in order to insert the element. So what is the average number of instructions? What is the total average instructions? The average number of instructions is going to be total instructions divided by total insertions. That how many elements you inserted. Now just think about it. 1 plus 2 plus 3 plus 1 plus 5, so on and so forth. 1 plus 2 plus 3 plus 1 plus 5 plus 1 plus 1 plus 1 plus 9 plus 1 plus 1 and so on. Whole divided by n, considering that you inserted n elements total. Right? Okay. Now if you see, this algorithm is performing very good. 1, 1, 1, 1, 1. And the higher the size of the array, more will be the number of insertions with operations equal to 1. Just think about it. Once we have done it, now after 90, 100, 110, 120, 130, 140, 150, all of these are going to be inserted with one operation. And once the array is full, then only you will double the size of the array, and that will be an expensive operation. So the expensive operations are less compared to the efficient ones, right? Okay. Now if you just carefully see, how can we simplify this? How can we simplify this? Can I write 2 as 2 raised to the power 0 plus 1, 3 as 2 raised to the power 1 plus 1, 5 as 2 raised to the power 2 plus 1, 9 as 2 raised to the power 3 plus 1, and so on. So I can replace 1 plus 2 raised to the power 0 plus 1 plus 1 plus 2 raised to the power 1 plus 1 plus 1 plus 2 raised to the power 2 plus 1 plus 1 plus 1 plus 1 plus 2 raised to the power 3 plus 1 plus 1 plus 1 and so on. Whole divided by n. Right? Okay. So can I say that in every term, in every instruction, you have definitely 1 as the term. See, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. So in every instruction, you have a term of 1. Can I say that? So if I segregate out all the ones together, how many ones will be there? Can I say there will be n occurrences of ones? Why? Because in every number you have an occurrence of 1. So if there are n iterations or n insertions that are done, there will be n terms of 1 plus something like 2 raised power 0, 2 raised power 1, 2 raised power 2, 2 raised power 3, and so on. Whole divided by n. Okay. Now what is 1 plus 1 plus 1 plus 1, so on and so forth, plus 1 n times? Can I say it is equal to n? Plus. What is 2 raised power 0, 2 raised power 1, 2 raised power 2, 2 raised power 3? Can I say it's a geometric progression? Can I say it's a geometric progression? And how many terms will be there? How many terms will be there? Just think about it. Let's say at last we will require, let's say when the size of the array will become n, so we will require some n operations, right? Which will be approximately somewhere around 2 raised to the power some value k, because you see every big copy that we are doing is around 2 raised to the power k. So if 2 raised to the power k is equals to n, can I say k is approximately equal to log n? So can I say there will be approximately log n terms? And what is the sum of this GP for log n terms? It is equals to first term into ratio multiplied by total number of terms is what? Approximately log n, right? Minus 1 upon 2 minus 1. 2 minus 1 is 1 only, so I'm not writing it, divided by n, which is equals to what? N plus, what is 2 raised to the power log of n to the base 2? N only, minus 1 by n, which is what? 2n minus 1 by n, which is what? Constant. Can I say that? So technically, if you individually see these operations, with asymptotic analysis, you will feel like the best case is omega of 1, the worst case is order of n, right? And on an average also it works for order of n, because these are very expensive operations. But if you see it with respect to amortized analysis, where we actually saw the total instructions divided by total insertion, that we actually calculated the mathematical average, then on an average, if you see, you have done n insertions. So for n insertion, the average number of instructions is constant. That means the time complexity for this kind of implementation is constant on an average. Yes, it is expensive sometimes, but if you see with it with respect to n, like a very large value n, then it's approximately constant. So even if you are copying n elements sometimes, but a lot of time it is performing very efficiently, the overall complexity of the algorithm is constant. And that's what we derived here. We just totaled the total number of operations. So 1 plus 2 plus 3, so on. We then divided these terms with respect to power of 2. And when you divided it with respect to power of 2, every term got a 1. So total ones that are present is n. And these power of 2 are log n. If you just solve it, you will get this term, which is technically what? Constant. 2n minus 1 by n is what? 2 minus 1 by n, which is technically constant. Hence, if you want to implement a dynamic array that has been implemented in these languages like modern languages like Ruby, JavaScript as well, using static arrays which are of fixed size, what you can do, you can double the size of the array, do this copy operation, and the overall complexity to insert an element in these arrays are going to be constant. And that is why when we push an element to the array, we don't bother about it because everything is going to be fine. But the main important point is this algorithm only works for push and pop from last. Like this algorithm will work for removing the elements also. When you're removing, and when let's say instead of doubling the size of the array, you can just do half the size of the array, right? But this will only work if you are doing the operations at the last. If you're trying to do the operations on the first, like on the start of the array, if you're trying to do the operations on the start of the array, let's say array is full, and I want to insert an element here. Now that is always going to be order of n, because there is no way other than you creating a new array. Even if let's say you create an array of size double the original array, let's say even if you create a 12 size array, then also you have to shift every element by one spot, right? So 1 2 3 4 5 6, and then you will let's say insert 0 here. Now if you want to insert one more element, let's say I want to insert -1, then we have a space, but we have to shift all the elements. Shifting all the elements will always take order of n, right? Shifting all the elements will always take order of n. It's not like we have space, so we are just directly inserting. That's not how it is done, right? So this algorithm only works that we have discussed if we are inserting the element at the last or removing the element from the last. So I hope the overall logic of amortized analysis is clear to you, that in this analysis, we take the actual average by considering the total operations, or total instruction by total operations. And then we decide that whether the algorithm is efficient or not. We just don't directly see the worst case or best case, but instead we do more mathematical analysis here. So there are a lot of algorithms, like apart from this also, there are a lot other algorithms also in which amortized analysis works absolutely fine.